Welcome to the Cybertruck unveil.
This isn't just another pickup truck. This is the Tesla Cybertruck, a product that dares to be different. With its distinctive angular design, an exceptionally durable stainless steel exoskeleton, and advanced technological features, this vehicle offers a unique driving experience.
Technology. Exactly.
Here's something that'll blow your mind. It takes this beast just 3 to 7 seconds to hit 60 miles per hour from a standstill. Yeah, you heard that right. For all its engineering genius, the Cybertruck's design still turns heads and divides opinions.
Is the way it makes other people around you on the road?
Anyway, join us as we explore the story behind the creation of this remarkable machine. And let's see how it's paving a new path for the future of transportation. The idea for the Cybertruck first appeared in 2019 when Tesla showed a pickup that looked nothing like the classic American trucks seen on highways for decades. The company wanted a vehicle that used simple flat steel panels instead of curved body parts. This choice came from aerospace work because similar stainless steel sheets were used on early space programs. Pickups have long been a part of American life, from farm fields to construction sites, so a truck built from cold-rolled steel quickly drew attention. Tesla chose a 300 series alloy because it resists rust and keeps its shine without heavy coatings. One interesting detail is that the exoskeleton design reduces the number of external body pieces compared to a standard pickup. This helps the factory focus on strength rather than complex shapes. The first major step forms the front and rear gigacastings. These huge parts begin as molten aluminum that is pushed into steel molds by a press capable of 9,000 tons of force. The molds cool the metal within seconds, which locks in the shape and keeps the walls within a millimeter of the target size. The castings include channels for wiring, suspension points, and large hollow spaces that help reduce weight. Sensors track the temperature of the aluminum as it flows, because a drop of only 50 degrees can create weak spots inside the part. Robots lift each cooled casting and scan it with lasers to confirm its exact shape. A fun detail is that one gigacasting replaces more than 70 parts from older pickup frames. This change removes hundreds of welds and shortens the build time on the line. So how does Tesla connect these giant pieces to the main cabin structure? The cabin takes shape in a stamping area filled with presses that strike sheets of steel with loud rhythmic hits. The presses form door frames, side rails, and roof supports from a mix of high-strength and ultra-high-strength steel. Each sheet moves through several stations, and every station adds a bend or a fold that locks the shape in place. The cabin structure is welded together on a moving platform. Sparks fall as robots complete hundreds of spot welds per minute. The finished cabin looks light, with large empty spaces in the floor and roof that are designed to hold the battery pack and roof glass. These empty zones play a major role in keeping the truck stable at high speed. One interesting fact is that the cabin and the gigacastings ride on separate floors before they meet. Elevators move the structures up and down inside the factory. So how does the shiny stainless steel skin attach to this internal skeleton? The exterior panels start as flat stainless steel sheets cut from cold-rolled 300 series alloy. The sheets are around 2 millimeters thick and can only be bent, not stamped. So Tesla uses long press brakes to create clean, straight folds across each panel. The machines push with enough force to shape the steel without heating it. The front lid has a gentle curve that improves airflow over the truck. The side panels have shallow angle bends that add strength without adding weight. Each panel connects to an aluminum support structure hidden beneath the surface. The mounts use brackets and fasteners placed on the inside so the outside stays completely smooth. A fun detail is that the bed panels are sprayed with a carbon composite liner before installation. This coating protects the steel from tools, gravel, and heavy cargo. So what fills the large empty space inside the truck once the exoskeleton is complete? The subframes carry the most important systems for driving. Each subframe holds an electric motor, a gearbox, a set of axles, and the suspension towers. Workers install the electronics and cooling lines before the frame leaves the station. The Cyberbeast version uses 3 motors, with 1 in front and 2 in the rear. The battery pack is built as a structural unit using 4,680 cells. The cells are arranged between steel plates that spread loads across the pack. The pack forms part of the truck floor, and the front seats bolt directly to its top surface. A conveyor moves the pack under the cabin structure, while a lift raises it from below. Robots tighten bolts to specific torque values so the pack becomes a locked part of the frame. This design helps increase rigidity and reduces vibration during driving. So what final pieces close the truck and give it its finished shape?
Oh my God.
The windshield arrives in large crates and moves through a special handling area. This sheet is the largest piece of automotive glass in the industry. It is thick and slightly curved to support the heavy roof. Workers guide the glass onto a line of sealant that holds it in place when the cabin frame lowers onto it. Doors are built separately. Each door uses a stainless steel outer panel and an aluminum inner panel that are joined by laser welding. Hinges, locks, and wiring are added before the door meets the truck. The tailgate and bed walls follow the same process, with their panels attached after the composite liner dries. The last stations add plastic covers, wheel wells, and wiring checks. Lights turn on and off. Water sprays across the truck to check the seals. The line moves slowly as inspectors confirm that every piece is aligned. So how does the next product take shape on this busy line inside the Texas factory? Over 70% of the machines inside modern factories run on electric motors, according to the International Energy Agency. These motors lift steel beams, turn conveyor belts, and move robotic arms with exact timing. Some are small enough to fit in your hand, yet they can spin at thousands of revolutions per minute without shaking. Others weigh more than a car and work for years with almost no rest. A fun fact is that the tiny gap between a rotor and a stator is often only 0.3 of a millimeter. So how do factories build a device that must stay this precise while pushing so much power? Electric motors trace their roots back to the early 1800s, when inventors like Michael Faraday and Thomas Davenport began turning electrical energy into motion. Their first designs were simple spinning coils, but they proved that electricity could power machines. By the late 1800s, factories across the United States were replacing steam engines with electric motors because they were cleaner, smaller, and easier to control. This change helped shape modern American industry, from steel mills to car plants. During the 20th century, new materials and better manufacturing pushed motor performance even further. Laminated steel reduced heat loss. Stronger copper wire allowed higher power without overheating. CNC tools made motor parts more precise and consistent. A fun fact is that many early workshop motors stayed in service for 50 years because they ran at low speed and were built with very thick steel. So how do modern factories turn raw metal into the motors that power today's machines? The first step creates the shaft, which is the central spine of the motor. Workers select steel rods from storage racks and load them onto the cutting line. A saw trims each rod to the exact length needed for the model being built. The pieces then move to CNC machines, where computer-controlled tools shape the metal. Cooling emulsion flows over the spinning cutters and keeps the steel near room temperature during machining. Each pass forms a shoulder, a groove, or a taper that helps the shaft fit tightly inside the rotor. Precision is critical, so laser gauges check the shaft while it rotates at slow speed. Even a small error of 1/100th of a millimeter can cause vibration when the motor runs. After shaping, the shaft is polished to remove sharp edges that could damage bearings. A fun detail is that the shaft often includes a tiny keyway that locks the rotor in place during high torque loads. So how do factories create the rotor that spins around this perfect steel core? The second step forms the laminated steel stacks that become the rotor and the stator. Large coils of thin steel feed into stamping machines that press out circular blanks at high speed. Each blank contains slots for copper bars or wire coils, depending on the design. Workers stack hundreds of these thin sheets on alignment pins to create a solid pack with smooth walls. The rotor pack is clamped in a mold and filled with molten aluminum that flows into the slots. The metal cools quickly and locks the rotor bars into place. Humidity must stay low in this area because water vapor can create gas bubbles in the aluminum. Any trapped gas weakens the rotor and reduces efficiency. After cooling, the shaft from step 1 is pressed into the center of the rotor. Stators follow a similar path but stay hollow for winding. A fun fact is that these laminated sheets help reduce energy loss by keeping magnetic fields from spreading through the iron. So what fills these stators and allows the motor to produce turning force? The third step adds the copper windings that generate the magnetic field. Workers begin by lining each stator slot with Nomex and Mylar insulation. This thin paper protects the copper from sharp steel edges. Spools of enamel-coated copper wire feed into winding machines that guide the wire with slow, steady motion. Some large motors need coils that are shaped by hand, while smaller models use fully automated equipment. Each layer of wire sits tightly inside the slot and builds a powerful field when current passes through it. When all coils are in place, technicians connect the leads that form the 3 motor phases. They then lace the coil ends with strong cord to prevent movement during high-speed rotation. Stators can take anywhere from 2 hours to 2 weeks to complete, depending on size and power level. A fun detail is that larger motors often use rectangular copper wire instead of round wire to improve space efficiency. So how do these wound stators become strong enough to survive heat, vibration, and years of non-stop use? The fourth step strengthens the windings through vacuum pressure impregnation. Bundles of wound stators lower into a sealed steel tank. A pump removes air from the tank and pulls resin deep into the coils. The pressure then rises, forcing the resin even further into the winding layers. When the tank drains, the stators drip dry for several minutes. They then enter an oven heated to around 200 degrees Celsius. The heat cures the resin and turns the windings into a solid block that resists vibration and moisture. After curing, each stator receives its housing. Aluminum housings are heated in a large oven until they expand enough to slide over the stator. When the metal cools, it shrinks and grips the stator tightly with no bolts needed. Cast iron housings follow a similar method, but often receive a primer coat for protection. A fun fact is that this shrink-fit method creates a joint strong enough to handle heavy industrial loads. So how do all these parts come together to form a complete electric motor? The fifth step brings every component to the assembly station. Workers place the housed stator onto a fixture and lower the rotor into the center. Bearings slide into position with a thin layer of grease to reduce friction at startup. End shields close the motor on both sides, and long bolts hold the frame tight. Technicians attach the fan, the conduit box, and any optional brake systems. The assembled motor then moves to the testing room. Test benches spin the motor under different loads and measure vibration, speed, and electrical performance. Thermal sensors track heat buildup as the motor runs at full power. Only motors that meet all specifications receive approval labels. A fun detail is that many factories store test data for years, so customers can trace the performance of each motor. So how do sensors and control systems get built to support devices like these? More than 60% of advanced driver assist systems rely on tiny sensors that fit on a fingertip, according to the National Highway Traffic Safety Administration. These devices track motion, measure distance, and capture images while the car moves at highway speed. Some read changes smaller than 1/10,000th of a degree, yet they work inside heat, dust, and constant vibration. A fun detail is that many MEMS motion sensors use micro-machined parts so small that thousands can fit on a single wafer. So how do factories build these precise eyes and balance systems that guide modern vehicles? The story of Autopilot sensors began in the late 1990s, when early MEMS devices entered the automotive world. These small chips could measure rotation and acceleration with better stability than older mechanical sensors. In the 2000s, car makers added basic cameras and radar units to support features like lane keeping and adaptive cruise control. Demand grew quickly as drivers wanted safer and more comfortable travel on busy highways. By the 2000s, sensor makers were building large clean rooms to produce millions of MEMS dies and CMOS camera chips each year. Engineers also developed new standards for safety. ISO 26262 became the main guide for designing hardware that must work under heat, shock, and vibration for many years. This shift helped bring reliable motion sensors, clearer cameras, and longer-range radar to the market. A fun fact is that some LiDAR units originally came from robotics labs before moving into cars. So how do factories turn these designs into real sensors that can survive life on the road? The first step begins inside the engineering lab, where teams define what the sensor must do. They set targets for accuracy, speed, and temperature range. Some sensors must survive -40 degrees in winter and over 100 degrees under a hot hood. Engineers select parts, write early firmware, and build documents that guide the whole factory. These documents include the bill of materials, safety notes, and the mask designs used in wafer production. Teams also check each design against ISO 26262, which is the main safety standard for automotive electronics. Prototypes are tested on rigs that shake, heat, and cool the sensor again and again. If the results drift too far, the design goes back for changes. This early work helps avoid mistakes on the factory floor, where thousands of units are built every day. A fun detail is that some calibration algorithms are planned long before any physical parts exist. So how do these designs turn into the tiny cores that give each sensor its abilities? The second step builds the sensing dies that sit at the heart of each module. MEMS motion sensors begin as polished silicon wafers that move into clean rooms. Photolithography tools shine ultraviolet light through masks to mark the wafer surface. Etching machines carve tiny beams, springs, and chambers into the silicon. A full wafer may go through hundreds of steps before packaging. Camera sensors follow a similar pattern, but produce millions of light-sensitive pixels across the surface. Radar and LiDAR parts use special RF, or optical processes that shape antennas or laser paths with extreme precision. Humidity, light levels, and airborne particles are strictly controlled in this area. Even a single dust particle can ruin a full die. After fabrication, workers cut the wafers into individual chips and test them one by one. Some chips stay bare, while others enter early packaging that protects the silicon. A fun fact is that a single wafer can hold thousands of IMU dies ready for assembly. So how do these dies become full modules that can attach to a car? The third step assembles the electronics and optical parts. Printed circuit boards move through surface mount lines where tiny components are placed at high speed. Reflow ovens heat the boards until solder melts and cools into solid joints. Workers or robots then attach the sensing dies to the boards. Adhesive or solder points keep each chip in the correct position. Cameras receive special attention because their lenses need exact alignment. Automated tools move the lens by micrometers while checking sharpness and color on a test chart. LiDAR units may receive rotating mirrors or small motors to guide the laser beam. Radar modules get RF shields to block outside noise. All parts stay inside clean areas to prevent dust from settling on exposed optics. A fun detail is that some autofocus units use tiny magnetic coils that shift the lens by only a few micrometers. So how do these modules receive the software and calibration that bring them to life? The fourth step loads firmware and tunes the raw measurements. Programming jigs contact each module through small pins. The device receives firmware that controls power, timing, and safety checks. Once the module boots, it enters calibration. IMUs sit on platforms that rotate through many angles, measuring gravity and movement in slow steps. The system records sensor bias and scale factors. Cameras face bright panels, color charts, and grids that help map lens distortion. Radar and LiDAR units run distance tests against reflective targets. All calibration results are saved to memory, so the sensor corrects itself during normal use. These values help reduce drift and increase stability on rough roads. Temperature chambers may heat or cool the modules to confirm that calibration holds across the full range. A fun fact is that some sensors store multiple calibration tables for different weather conditions. So how do factories make sure only the best units reach the assembly line? The fifth step pushes each module through strict tests. Environmental chambers cycle between freezing and high heat while the sensor runs. Vibration tables shake the units to mimic rough pavement. Salt spray tests check seals on sensors placed near the car exterior. Each sensor also completes functional tests that measure response time, accuracy, and signal strength. Radar units must read targets at different angles. Cameras must stay in focus. IMUs must keep stability under rapid rotation. When testing is complete, workers inspect the modules under bright lamps and pack them into anti-static trays. Serial numbers and calibration IDs are printed on each module, and all test data goes into secure storage. Car makers use this information when checking incoming parts at their factories. A fun detail is that some companies keep every test log for over 10 years in case of recalls. So how does this careful inspection help prepare sensors for their next journey onto a moving vehicle? From giant gigacastings to tightly wound copper coils to chips smaller than a grain of rice, these three products show how modern factories turn raw materials into the machines that move our world. The Cybertruck frame, the electric motor, and the Autopilot sensor each follow a different path, yet all rely on careful design, extreme precision, and long hours of testing. These processes reveal how much hidden work sits behind every smooth drive on a highway or every quiet lift inside a plant. Watching them reminds us that even familiar technology is full of unseen steps and skilled hands. If you enjoy learning how everyday products are made, remember to like the video, leave a comment, and subscribe to Captain Discovery for more factory stories.